Good day. Now we will be answering problems from Chapter 26, Direct Current Circuits or DC Circuits. We will answer problem numbers 26.54, 26.62, and 26.68. First problem, problem 26.54. In this figure, the battery has a negligible internal resistance and an EMF or electromotive force of 48 volts. Resistance 1 and resistance 2 is equal to 4 ohms and resistance 4 is equal to 3 ohms. What must be the resistance R3? B for the resistor network to dissipate electrical energy at a rate of 295 watts. To solve this problem, we will do series parallel reduction. In series connection, the total resistance is given by this formula, and in parallel connection, the total resistance is given by this formula. First, resistors 1 and 2 are both 4 ohms and they are in series connection. Therefore, by applying this formula, we will get 8 ohms. Next, this 1 and resistor 3 are in parallel. Applying this formula, we will get 1 over R12 plus 1 over R3 is equal to 1 over R123. Then lastly, for this 1 and R4, they are in series. Applying this formula, we will get R1234 is equal to R123 plus R4. We do not have value for R123, but we have value for R4. Since we do not have value for R123 yet, we can solve the resistance using this formula of power. So power is equal to EMF squared over R. Since we have the value for P and the value of the EMF. So finding R1234 or REQ of the network, or simply the R, we will substitute the values. So this is our EMF, 48 volts, and the power is 295 watts. Dividing the two, we will get 7.810 ohm. So this is the total resistance of the whole network. Now, finding R123, we will use this equation and rearranging this to get R123, we will have R123 is equal to the total resistance of the network minus R4. We already solved this one, the total resistance, which is 7.810 ohm minus 3 ohms, giving us the resistance of R123 of 4.810 ohm. Now, since we have the value for R123, we can solve now for it. Rearranging this to get R3, we will have R3 is equal to R123 multiplied by R12 over R12 minus R123. Substituting the values, we have the value for R123, which is this 4.810 ohm, multiplied by R12, which is this, R12 is this, and R123 is this. Then this will give us the resistance of the resistor 3, which is 12.1 ohm. Next problem, problem 26.62. Find the current through the battery and each resistor in the circuit. What is the equivalent resistance of the resistor network? To solve this, we will use Kirchhoff's rule. And according to Kirchhoff's rule, for junction, the summation of current is equal to 0. So the junctions in the circuit are this, and this. Next, for Kirchhoff's loop rule, the summation of voltage is equal to 0. We will assign loops in this circuit. For loop 1, we have clockwise. For loop 2, we have clockwise as well, and loop 3, we have clockwise as well. So this is our loops. Loop 1, loop 2, and loop 3. Let's first solve for the loop 1. So by using the sign conventions, loop 1, starting with the battery, we have positive 14, negative I1, negative 2 quantity I1 minus I2 is equal to 0. Rearranging this or distributing 2, negative 2 to I1 and negative I2, we will have 3I1 minus 2I2 which is equal to 14. Next, for loop 2, let's start with this 2 ohm resistor. Negative 2 quantity I minus I1 plus I2 plus I1 is equal to 0. Rearranging this and distributing negative 2, we will have negative 2I plus 2I1 plus I2 plus I1. Combining like terms and rearranging it, we will have negative 2I plus 3I1 plus I2 is equal to 0. Lastly, for the loop 3, let's start with this 1 ohm resistor. Negative quantity I minus I1 plus I2, then plus 2 quantity I1 minus I2, then minus I2 is equal to 0. Rearranging this, distributing the coefficients, we will have this as we combine the like terms. Negative I plus 3I1 minus 4I2 is equal to 0. Since we now have three equations from loops 1, loop 2, and loop 3, we can solve for the values of the current. Now, starting with loop 1 equation, we can solve for I1. And rearranging this equation to get I1, we will have I1 is equal to 14 plus 2I2 over 3. Next, using loop 2 and loop 3 equations, we can solve for I by subtracting these two equations because we can cancel 3I1 in this or from these equations. Then doing that subtracting the equations, we will get I is equal to 5I2. So this is the value for I, the value for I1. Then we can solve for I2 using loop 3 or loop 2 equation. This time we will use loop 3 equation, which is this. Substituting the value of I and I1 in this loop 3 equation, we will get this, negative 5I2 plus 3 quantity 14 plus 2I2 over 3 minus 4I2. So we can see that 3 can be cancelled, leaving us with this. Then combining like terms, we will get negative 7I2 plus 14 equals 0. And solving for I2, we will have I2 is equal to 2 amperes. Next, let's solve for I1. So using this I1 equation and substituting this I2 with its value. So the value of I2 is 2 amperes. Let's substitute it with this I2 and we will get this. Solving this, we will have I1 is equal to 6 amperes. Then lastly, for solving I, so we can input the value of I2 here. So our I2 is 2 amperes and we will multiply it by 5. Therefore, I is equal to 10 amperes. So we have the amperes or the value of current of I1, and I2. So the summary is I, which is this for the battery, is 10 amperes. Next, our I1 for this resistor 1 is 6 amperes. Next, our I2 for this another resistor 1 is 2 amperes. Now, let us solve for this current, and this current. So, substituting the values accordingly, we have IR2. IR2 is this, which is this current, and it is equal to 4 amperes. Next, IR4, this the IR4 is I1 minus I2, which is equal to 4 amperes. Then lastly, our IR5, so the current flowing in this resistor is this, I minus I1 plus I2, giving a value of 6 amperes. Then part B, what is the equivalent resistance of the resistor network? Solving the equivalent resistance of the whole network of resistor, we can use Req is equal to V over I. Our V is 14 and current is 10. Solving this, we have 1.4 ohm. So the equivalent resistance of the resistor network is 1.4 ohms. Okay, last problem, problem 26.68. Three identical resistors are connected in series, as shown in this figure. When a certain potential difference is applied across the combination, the total power dissipated is 45 watts. What power would be dissipated if the three resistors were connected in parallel across the same potential difference? So in solving this, we know that in series connection, the resistance will add up, and in parallel connection, the resistance is given by this formula. Since R1 and R2 and R3 are three identical resistors and they are in series, we can apply this formula and we will come up with Req is equal to 3R. Now, using the formula for power to compute the total power dissipated, we have P total is equal to V squared over Req. Since our Req is 3R, we can substitute it and get PS, or the power in series connection, is equal to V squared over 3R. Next, if the three identical resistors are in parallel, by applying this formula, we will get Req is equal to R over 3. Using the same formula for power, power total is equal to V squared over Req. And we will substitute Req with R over 3, and we will get P, or power for parallel connection, is equal to V squared over R over 3. Now, simplifying this, we will get P in parallel connection is equal to 3V squared over R. We know that this V squared over R is the formula for power. Therefore, we will have 9 PS, because this is the same power with the series connection. And substituting the value, so and multiplying this, we will get 405 watts. So this is the power dissipated if the three resistors were connected in parallel across the same potential difference.